Hello, Matthews Gatos here. In this video, we are going to look at lesson number 5, solving problems using tables and diagrams. So just to review with you what we've done so far, we've looked at odds to probability, changing between those two. So for example, if I have odds in favor, that's all the ways A can happen to all the ways A can't happen. I can take that and change it into a probability. The probability of A is all the ways A can occur out of the total, and the total is A happening or A not happening. We can have odds against, which is A no to A yes, and the probability of A not happening, A against A, would be all the ways A can't happen out of the total of A not happening and happening. We also looked at OR probabilities, and OR probabilities were mutually exclusive or not. So you can see mutually exclusive here, there is no overlap. So it's just the individual probabilities added together. Not mutually exclusive means that there is overlap. So since there's overlap, we have to subtract that overlap. So it's the individual probabilities added together, subtracting the overlap. And then the last thing we looked at was AND probabilities. AND means multiply. Those are the independent and dependent. So two events are independent if the probability of A and B happening is the individual probabilities multiplied together. Dependent events, if it's not equal to the probability of A times the probability of B, it's dependent. So then we have to look at the probability of A times the probability of B given A. And B given A here, that just means the probability of B if A happened first. So that's what we've done so far. So let's look at how we can use tables to help us figure out probability. So in this table we have students in high school. They were surveyed to see how do they get to school. So the information that we have is as follows, and it's split into male and female students. So of the students that take the bus, 350 were male, 300 were female. Of the students that come to school by car, 200 male, 175 female, and so on. So I want to finish off the chart by doing the totals. So let's look at the males, for example. To do the totals, I'll add 350 plus 200 plus 75 to get a total of 625. To get the total of the females, I have 300 plus 175 plus 100, 575 females. Now, adding that together will give me the total in the school of 1,200. So you'll notice that I just populated all of the bottoms here and made them into 1,200 because that's the total. Now, if this total is correct, it will also add up this way here. So if we look at the number that took the bus, that's 650. The number that took the car to school is 375, and the number that had another transportation was 175. If you add these up together, it also adds up to 1,200. So that's a nice little check. It has to add this way and also this way to the total. So now that we figured that out, let's do these probabilities. You'll notice I've cut off 2 of those questions that we're not going to do, not part of the curriculum. So the probability that a randomly selected person to survey was a male, so there's 1,200 in total. Let's look, how many of them were male? There were 350. So oh no, sorry, that's just the ones taking the bus, my mistake. All together, the males were 625. So 625 out of 1,200. Put that in lowest terms, you get 25 out of 48. Over here, the probability a student selected for the survey was male and traveled by car to school. So male and traveled by car, right there, that's the 200. So 200 out of 1,200, or in lowest terms, 1/6. Okay, and these ones here, a student is selected at random, determine the probability the student is female. So looking at female, all of these, my total there is 575 out of 1,200. So in lowest terms, that's 23 over 48. The probability the student travels by bus, so it didn't specify gender, so I'm going to take this 650 out of 1,200 and put that into lowest terms. And then the probability it's a female who travels by the bus, so a little bit more specific. So female traveling by the bus, 300. So I'm going to take that 300 out of 1,200 in lowest terms will be 1/4. Okay? Okay, continuing on this question. So this is the table that we filled out. These are some of the probabilities that we just figured out in part D. We're going to cross off part E. We're going to go to part F. Part F says are the events, the student is female and the student travels by bus, independent events? Well, if they are independent events, then the probability of female and taking the bus will equal to the individual probabilities multiplied together. So let's check. So we know from the last part the probability of a female that is also taking the bus is 1/4. We know that the probability of a student in this survey is female is 13 out of 24. We know a probability of a student taking a bus in this survey, 23 out of 48. So if I multiply those together and they equal to 1/4, then yes, it's independent. So I go to my calculator to help me. Multiplying those together, I get 299 out of 1,152. So these are not equal. So since they are not equal, they are not independent. So since they are not equal, being a female and riding the bus, not independent. Okay, let's try an example where we're going to use a tree diagram. So students were given the following problem to solve. The odds that Ava will pass math this semester are 4 to 1 in favor. The odds she will pass English are 1 to 9 against. So first thing we want to do is change the odds to probability. So if she has 4 to 1 odds in favor, what that really means is there's 4 ways she's going to pass to 1 way she won't pass. So pass, not pass, the total 4 plus 1 is 5. So the probability she'll pass math is the 4 ways out of 5 that she can pass. The probability she won't pass math is the 1 way out of 5. Now in this one here, we're given odds against. So odds against mean not passing English to passing English. So not passing English to passing English, okay? So looking at this, there's 1 way that I am not going to pass to 1 way that I will pass for a total of 10. So the chance of her passing English is the 9 ways she's passing English. The chance of her not passing English is the 1 way out of 10. Okay, so now we've expressed our odds as probabilities. Let's look at the next question. So if these events are independent, determine the probability to the nearest hundredth that she will pass math and pass English. So since she's passing both and they're independent, I can just multiply the individual probabilities together. So the probability of her passing math was 4 to 5. The probability of her passing English was 9 out of 10. So I just want to multiply those together and put them in lowest terms, and I get 18 out of 25. The next one, I'm looking at math and not English. So passing math and, meaning multiply, not passing English. So passing math, a 4 out of 5 chance. Not passing English, a 1 out of 10 chance. So multiply those together and put them in lowest terms. I get 2 out of 25. Okay, this one says pass math or English. So I already know that she can from part I here. I already know she can pass math and English, so I have to subtract that overlap. So I'm going to do the probability of math plus the probability of English minus the probability of both. So probability of math, 4 out of 5. Probability of passing English, 9 out of 10. And we already calculated over here the probability of passing both. So I have to subtract the overlap because I've counted it in the math and also in the English. So add the two together, subtract the overlap, and I get 49 out of 50. Okay, let's put these on a tree diagram. So another way of solving this question is through a tree diagram. So probability of passing math was 0.8. So therefore the probability of not passing math, if I have a probability of passing math is 80%, then not passing math would be that 20%. Now that's for math. Now she could pass math, and then moving on from there, she could pass English or not pass English. Over here, she could pass English, 0.9, or not pass English, which is 0.1. Okay, so it branches out again. These are all complementary. Math and not math, complementary. English, not English, complementary. English, not English, complementary. So to figure out the final probabilities, I follow along my tree diagram. So this is passing math and passing English. Multiply them together. This branch is passing math and not passing English. Multiply them together to get that chance. This one is not passing math, but passing English. Multiply those together. And this branch, the last branch, not passing math, not passing English. Multiply those together. Now, I always like to do a really quick check just to make sure, do my probabilities add up to 1? And they do. So now that I have my tree diagram filled out, I can answer those questions. So looking at this one here, again, they are independent, so I want to answer the questions. So determine the probability she will pass math and English. So I want to pass math and also pass English. So that's just the 0.72 there. I want to pass math and not English. Math and not English, 0.8 chance, 0.08, 8%. Math or English. So I can look at passing math or English or both. So here's passing both. Math, passing math, but not English. Passing English, but not math. So math or English or both. And I would just add those together to get 0.98. So you've seen solving that question in 2 different ways, with the table and with the tree diagram. Okay, in this next question, we're going to fill out the tree diagram ourselves. So in a game of field hockey, the probability that the Dinos score a goal from any short corner is 1 out of 8. During the first half of a match, they get 2 penalty corners. Use a probability tree to determine the probability from these 2 short corners that the Dinos will score. So on the first kick here, 2 branches, one for the first kick and the next one for the second kick. If they have a 1 out of 8 chance of scoring, they must have a 7 out of 8 chance of not scoring, because these are complementary. Okay, so if they score, it branches off into they could score again, 1 of 8, or not score, 7 out of 8. So here, if they miss the first one, they could score the second or not score the second. So then what I want to do is read along these pathways. So score and then score. So that's going to be score and then score. I'm going to multiply those together. So 1 out of 8 times 1 out of 8, and that is 1 out of 64. On my next branch, I can score the first, but miss the second. Score the first, miss the second. Multiply those individual probabilities together. 1 out of 8 times 7 out of 8, and I get 7 out of 64. Okay, here I could miss the first one, but score the second. Multiply those individual probabilities together, and I will get 7 out of 64. And then the last one is they miss both. They don't score either. So multiply those individual probabilities together, and I get 49 out of 64. So first thing I want you to notice is that each branch adds up to 1 because they are complementary events, and I check to make sure that the total adds to 1 as well, and it does. Okay, so now based on this, we can determine the probability they get both the goals. So that's score and score, that's 1 out of 64. The probability that they get 1 goal. So 1 goal here, they score and not score, but they could also get 1 goal here, 7 out of 64 as well. So what I'd have to do is just add those together and put it in lowest terms. So 7 out of 64 plus 7 out of 64, my answer here would be 7 out of 32. Okay, at least 1 goal. At least 1 goal means 1 minimum. So they could, in this case here, there's 2 goals, or 1 goal, or 1 goal. Basically everything except for this last one here. So I'm going to add those together because those are the cases. This is both getting goals, the first one but not the second but not the first. So I can just add those together, and then the answer for C would be 15 out of 64. And then the last question says, what is the chance they have no goals? Well, that's just the 49 out of 64. So pretty much a better chance of getting not goals than anything else. Okay, let's look at a tree diagram for dependent events. Okay, so we have an example here where we have 2 machines, A1, A2. They produce glass bottles made in a factory. The percentage of broken bottles produced by these machines is 5% for A1 and 8% for A2. Machine A produces 60% of the bottles. So we want to create a tree diagram because there's 2 things going on here. First of all, what factory are the bottles coming from? Secondly, will they be broken or not? So I'm doing this in a little bit of a different format than is in your workbook, just because I think this makes a little bit more sense. So first of all, the choice is, does it come from factory A, or does A1 or A2? So if there's a 60% chance that the bottle comes from factory A1, there is a 40% chance it comes from A2, because these are complementary events and have to add up to 100. Now, if it comes from A1, the chance that it will be broken, 5%. So since these are complementary, broken or not broken, there's a 95% chance it won't be broken. If it comes from factory A2, there's an 8% chance it will be broken. Since these are complementary, broken or not broken, this would be 92%. So they have to add up to 1. So again, to highlight, everything on my branches, those two have to add up to 1. These two have to add up to 1. These two have to add up to 1, because they are all complementary events. Okay, so let's put this together. The probability it came from factory A1 and it's broken, multiply those together. The probability it came from A1 and it's not broken, multiply those together. The probability it came from factory A2 and it's broken, multiply those together. The probability it came from factory A2 and it's not broken, multiply those together. Now, if I've done that correctly, I always check to make sure that my total adds up to 1, and it does, so I'm good to go. So now that I've done my tree diagram, I can answer some questions based on that tree diagram. So there's my tree diagram. Okay, so we're going to ask, Cheryl asked John some questions to see if he understood what he drew. If a bottle is chosen at random, determine the probability that it is a broken bottle produced by machine A1. So machine A1 and it's broken. Machine A1 and it's also broken. So there is a 3% chance. We're going to omit part 2. Part 3 says, if a bottle is chosen at random, determine the probability the bottle is not broken. So I'm going to look for all the not brokens. Like right here, this is factory or machine A1, not broken. This is that it's produced by the machine A2 and it's also not broken. So it could come from this one, or in math means add. We add those together and then I get this, a 94% chance that the bottle is not broken. Okay, let's look at this one here. So as a part of an experiment in the learning process, a mouse is put into a maze and rewarded with food every time it turns right. So we're trying to see, can we train the mouse to always go right? So if a mouse turns right, the probability it turns right the next time is increased by 20%. So at first I have a 50-50 chance of it going left or right. But if it turns right, it increases by 20%. Now that does not mean you do not go 50% plus 20% is 70%, because that's not increasing by 20% of the original choice or chance of it going right. So this would not be wrong, okay? Because it's increasing by 20% of the original amount, okay? Whoa, there we go. Let's try that again. I'm trying to cross that out. That's wrong, okay? So what this really is the original 50-50 chance, 50% chance, plus an extra 20% increase. So I'm increasing it by 20% of a number. Let me just get rid of this here so you can see my note. Okay, so 20% of a number means 20% as a decimal multiplied by the number. Since it's increasing, I'm adding. Now, when I do that, 0.5 plus 0.2 times 0.5, I'm going to get 0.6 altogether. Okay, over here, if the mouse turns left, doesn't get any cheese, so the chance that it turns left the next time goes down by 20%. So I'm going to do the same thing, but I'm decreasing this time. I'm going down by 50% to get 0.4. So I want to put this all into a tree diagram and just looking at the first 2 turns. So the first turn can be right or left. Notice that they add up to 1 because they're complementary. If it goes right the first time, he could go right or left the second time. Again, those add up to 100 or 1. So the probability of going right and then right, multiply those together, 0.3. The probability of going right and then left, multiply those probabilities together and you get 0.2. The probability of going left and then right, and then the probability of going left and then left. As I've done before, always check to see that those totals add up to 1, and they do. So now that I'm done my tree diagram, I can answer some questions about that. Okay, so what is the probability that the mouse goes both to the right? So right and then right, that's 0.3. What's the chance the mouse goes both to the left? Left and left, 0.2. What is the chance that the mouse does different turns? So right and left, that's different. Right and left, that's also different. So I'm going to add those numbers together to get 0.5. Okay? So again, when I'm saying different, it could be left and right or right and left. You have to look at both the cases. So let's summarize this. When you're using tables, probability tables, make sure the total of the columns is the same as the total of the rows. When you're using tree diagrams, make sure you multiply from branch to branch. And I have a little diagram here, branch to branch, multiply the probabilities, okay? And since each branch of a tree diagram is a complementary event, make sure the total is always 1. Okay, so question answered or asked on a quiz, make a tree diagram showing all possible sandwich combinations using one type of bread, one type of meat, one type of cheese. You can choose from white or rye, turkey, beef or ham, cheddar or Swiss. So we want to know, using a tree diagram, how many combinations are possible. I'm going to let you do that on your own, and you can check back for the answer, see if you get the same answer that this student got in their beautiful tree diagram. Okay, hope this lesson helped. I'll see you for the next one. You guys can work on your practice questions, and we'll see you soon.